And I'm just gonna, if you don't mind, I'm gonna quickly bring up that spotlight again. Here is our Michael Tanner. We're really excited to have him tell us about algebraic design of quasi-cyclic LDPC code, something I'm really excited to hear about because it brings together two topics in coding theory that are often understood to be separate, but today we'll bring them together. So go ahead. Thank you very much.
Thank you, Rick, for the introduction. And it's great to be virtually there at UCLA, a place I've been many times since I was affiliated with the University of California for a long time. About a dozen years ago, I withdrew for the second time from being a coding researcher to get back into being a full-time university administrator. And then eventually I retired for, I think, the final time. And I was working here on various projects at home, and COVID-19 hit. And suddenly I had a great deal of concentration time available to me. And I said, well, there was an idea that was intriguing to me from back actually in the 1980s that I'd never gotten the time to really pursue. So I started taking that up. And what you're going to hear today is sort of the fruits of that, of those contemplations and that research during that period. So I'm going to start sharing my screen. And let's see, where does it go? Right here. And I'm hoping you're seeing the full screen version. Yes, okay, I hope that's good.
We're seeing the slide, we're seeing like the slide manager version.
The slide manager version. So let me
get swap. Yeah.
Swap this around.
Now it's perfect.
Okay, now we got it. Maybe I can do a little more. Okay, well, I'll go from there. So this is expanding based on interactions that I ended up having with Darius Gibsalar on a paper that I had prepared for GlobeCom that's coming up at the end of this month or beginning of December. I'm going to give you a whirlwind tour of error correcting coding from my perspective, kind of say what my objectives were in doing this work, which is to see if I could get higher quality codes with considerable simplification of the description of the codes and the circuitry. I use an algebraic design technique. Rick mentioned that the style of construction these days doesn't use algebra very much as opposed to the early years, but I've got an intermediate where you can try to take the power of algebra to create graphs that create good codes. I'll give you an example of a code created from what I call a single orbit. Then I'm going to look at a number of rate 1/3 codes. I worked on rate 1/3 just as examples. You're not restricted to rate 1/3, but I did a number to show kind of the range of what you could do, and then some codes of other rates, including one that is of the style that you've been of interest, has been of interest to people out there, which is rate compatible codes, and then some simulation results, the simulations having been performed by Darius Gibsalar. So long ago, in algebraic coding, which was dominant from the beginning up until 70s and into 80s, you defined a code as a linear subspace of vectors. You borrowed from mathematics to be able to prove the minimum distance of the code, that separation between, closest separation between any two code words. And they used mathematics very fruitfully to come up with some great codes. Reed-Solomon codes that are on CDs and DVDs, I guess, BCH codes that are very versatile, algebraic geometry codes. So you had some great codes that are extraordinary in terms of how they pack the space, the Golay codes, for example. You also had convolutional codes, which were well adapted to continuous transmission. And Andrew Viterbi came along with a technique you translate from other domains, and it's not entirely novel in its structure, but it was very, very powerful for using soft decision information to optimally decode when you had a convolutional code with a certain state space. They were great for noisy additive white Gaussian noise channels. But both approaches had some limitations, the first being the complexity of decoding for these algebraic codes, the number of steps, And they were tremendously awkward to when you asked to take advantage of soft decision information, which could get you closer to the actual capacity of a channel like the additive white Gaussian channel. On the other side, you had the same issue, complexity of decoding. As the number of states goes up, the complexity goes up, and it goes up effectively exponentially. The result is that those convolutional codes, from a certain perspective, were actually weak codes. Now, there's a UCLA connection here. I remember going down and talking with Jim Omura when he was on the faculty at UCLA and trying to interest him in my style of coding of these graph-based decoders with the argument, yes, it's true that the Viterbi decoders are optimal decoders, but you're using an optimal decoder on a really weak code. Wouldn't it be better if you had a really strong code and you might be able to get along with a suboptimal decoder because you've got a very strong code, right? And Jim said, well, that's intriguing, you know? That was his view. So then came turbo codes, which they took two convolutional codes. This is Claude Berroux, Alain Lervieux, and their postdoc Didimashima. And they said we can link two convolutional codes together with an interleaver, and we can use iterative decoders that pass probabilistic information about the bits, and we get some really great performance. It really creates a block code out of what used to be this continuous infinite transmission, because once you have an interleaver over a certain space, now I know that they're moving, so that's not the case, but if you have a finite interleaver, that's what you've got. But they really stunned the world because they showed that they could get close to Shannon limit performance, and everybody said, oh, really? Let's check this out. That's quite amazing. Is it really true? You know, and the wonderful aspect of science, they could check it out and it was true, right? And so suddenly everybody shifted around. Now, from my point of view, it was very nice because it brought attention back eventually with the work of Nicholas Viberg and Andy Lulliger to looking at codes as bipartite graphs and using message passing decoding to solve the system of coding constraints. And for the most part, at this point, it's still a lot of concentration on the pure parity check, but you can do other things as well. So here's a low density parity check code. This is work of Bob Gallagher in his PhD thesis. And low density just means in a big parity check matrix defining the parity checks that operate on the bits of the code, you have very few ones. Now, when is a density low density? Well, it's kind of hard to say. There's not a formal definition really of what you would call low density that I'm aware of, because it depends on whether or not it's low enough density that you can get iterative decoders to actually decode on it. And then you can say, okay, I've got a low density. You can view this H matrix as an incident matrix for a bipartite graph, where every row defines a check node and every column defines a bit. And here I've shown bit nodes on the right, check nodes on the left. And then you put in an edge between the check node and the bit node if there's a 1 in the parity check matrix. That style of code with very few edges, which is say the low density property, allows you to do this iterative decoding that I'll describe. But one of the things you are looking for is cycles. And here I'm showing a cycle in the graph, a set of connections among bits that form a cycle of length 6. And for those of you who are not fully steeped in this, if you have short cycles, it means that information gets repassed and recirculated and it's no longer independent. And all the wonderful proofs that require independence fall apart. So you actually are trying to avoid short cycles. But they have these efficient algorithms. So the first stage, you can take the log likelihood ratio for a bit as received from the channel. You pass that to the adjacent checks in the graph. And then you can do local Bayesian computations, updating the log likelihood ratios for each of those bits once you've started from the received values from the channel. And it's got sort of 2 phases and their various forms. The flooding algorithm, all of them pass their information about their current view based on the information they've been receiving from other nodes and whatever they started with to a check node, and the check node can then update a Bayesian computation for another attached bit node. And similarly, on the other side, you have information coming from checks saying what they think based on information elsewhere in the graph, they think this bit should be, and that can be updated to tell the next parity check, well, now I've updated what I think my current state is. So it's what I'd call a local Bayesian computation. And it turns out that those can do very well. When I looked at this graph algorithm long ago, I was really quite thrilled with it, because if you think about all these bits putting their information in and then putting it out, it gives it the property of the fast Fourier transform. It's very efficient in terms of the computations that are taking place for passing the information around. So there was a breakthrough that occurred in late 90s, I guess I would say, in terms of analyzing how these codes worked. How do you prove that an algorithm that's constantly updating these log likelihood ratios based on information coming from other bits, how do you prove that it will converge to the right answer? And a really beautiful piece of work by Richardson and Urbanki was to say, we can think of what those log likelihood ratios doing as having a probability density of what your current state of it is. Based on these other things, you're updating that probability density for the log likelihood ratio. And it evolves over time as it moves up in a tree-like structure. And you can prove the algorithm will converge. And it's probably been refined beyond what I know. I've been, as I said, sort of out of coding for a dozen years or more now. So I probably don't know lots of things that are been said. But the way they got there is by analyzing random ensembles. And that was a brilliant way of thinking about solving this problem for the infinite tree structure. Said build graphs that have very large girths if you want this tree structure to be actually valid as a reflection of the structure of the code, and then this density evolution will work. But I guess people found fairly quickly that you could sort of cheat even on a finite graph. The density evolution worked pretty well, and maybe again that's been done. But I had this little lingering question when I saw that work: is whatever happened to minimum distance? When I first started working on it, everybody said, "Well, we won't even talk to you unless you can say something about the minimum distance." And suddenly, minimum distance disappeared. Other than the fact that over the ensemble, you knew you could have codes with good minimum distance. But there's always that question of, well, but the one that you actually construct, the one that you're about to put on the spacecraft or whatever, are you sure you know? And I think the answer is, and you can correct me, that for the most part, you make sure by simulating. So there have been lots of advances in this low density parity check code construction since it got going, different ways of constructing graphs with large girth, protographs and lifting. I did lifting of graphs in the late 1990s myself. They refined analysis of finite length behavior, graphs adapted to specific channel needs, like the digital fountain concept and Raptor codes. And you have spatially coupled, which is effectively the convolutional version, I guess, the language that's used for that. I'm quite interested in what UCLA is doing with the protograph-based Raptor-like rate-compatible codes. And I've gotten into a nice dialogue here with Dariush. So what my objectives in doing the work were to design LDPC codes using some algebraic structure to simplify the codes without, you hope, losing all those properties that randomness allows you to prove about growth in the minimum distance over time and the effectiveness of the algorithms. I want to use algebra to come up with powerful ways of understanding the girth and the diameter of the graph. I'd like to see if I can get some bounds on the minimum distance of the code and see if I could get better weight distributions, few cycles and very few close code words. And ideally show that you'd get at least the waterfall region performance comparable to current construction techniques, and maybe a better error floor if you can get a better minimum distance. So those are the things that were motivating me. So here's the overview. I'll talk about these quasi-cyclic codes. They're based on block circulants that are not only invariant under the cyclic shift, which is what you mean by circulant, but they're invariant under the action of another subgroup, the multiplicative group mod P for P a prime. Doesn't actually have to be a prime, but it's hard to work if it isn't a prime. So I'm going to just talk about P today. I'm going to impose this automorphism group that enables me to design codes by what I'm going to call orbit selection. I'll show you some examples of these rate 1/3 codes. They're based on a 2x3 block matrix of circulants of size P, and look more closely at two variants. And then I'll show you some codes of other rates, including one that's of the rate compatible style. And just say that some of these codes have really had very good minimum distances, given that they're intended to be sparse, and then give you simulation results, which are thanks to Dariush Ipsilar. So here's a way of looking at circulants. How long do we have to go? How much time we have here, Rick?
You can, our seminar is typically an hour, so until
Okay.
10.
And I'll try to keep rolling. You can think of a circulant matrix as having a property defined by a permutation matrix that performs a cyclic shift. So here's a permutation matrix that if you take a vector from the left and multiply it, it will cyclically shift that vector one place to the right. And then, of course, you can have its inverse, which is its transpose, and shift things back. Okay. The circulant matrix has the property that you can multiply by this permutation and take it through H and then multiply by the inverse, and it's the same thing as H. Okay. You say when that is the case that this permutation is in the group generated by these cyclic shifts is an automorphism group of the matrix H. Okay. So this is nothing new if you're used to circulants. This is just a way of saying what the circulant is. You can shift the vector over, pass it through H, and then shift it back, and you get the same answer. And that's because H has got that cyclic shift property itself. That's a way of expressing it. Now, if you have a set of matrices that have a common automorphism group, like their automorphism group is a cyclic shift, it's preserved in matrix algebra. So here's what happened, for example, if you have two matrices, an HA and an HB, both of them have this property, right, that they have the cyclic automorphism. You look at the product, you can substitute in, this is the identity matrix, and there you see that C, the product, has the same automorphism. So the automorphism is preserved when you do the multiplication. Circulants beget circulants, which is why a lot of coding theory is based on cyclic codes. It simplifies the world. I'm interested in another group, which is, again, nothing terribly deep. It's well known in as group theory, but it's the group of multiplications in the Galois field of arithmetic mod P. So I don't know how much people have had algebraic kinds of stuff, but if you perform arithmetic mod P, always taking mod P, that forms a field, and you can do arithmetic just like you're used to, because there's always going to be an inverse for every element. You can multiply two elements. Just take, here I'm using the prime 13. You can multiply 4 times 3 and you get 12, okay. And well, there's 12. If I multiplied 8 times 6, I'd get 48, and then I'd have to reduce it mod P, but I can do my standard arithmetic and everything behaves the way you'd like.
Can you show us the previous slide for just one more second?
Sure.
I'm just the last. So your point here is that if I multiply two parity check matrices that satisfy that same automorphism, then I get another matrix that also satisfies the automorphism.
For the time being, eventually I'll use these as blocks in an actual parity check matrix.
Okay.
Okay, so these, just think of it as a little block. It's a matrix that is a circulant. And it just says if you take two of these things that have an automorphism and it's in common, when you multiply them, that product will have it. Or if you sum two, so the sum will have the same.
Oh, sure. I mean, that's another way of thinking of it is if I cyclically shift by 2 and then cyclically shift by 3, I multiply those two things together, that's cyclically shifting by 5.
That is the same thing as looking at the elements of the group, right? That's in the automorphism. But if I take two things that have that property, both of them, you know, a circulant, it's each row is the shift, right? The cyclic shift. And you multiply two such matrices, the product has the same property that each row is a cyclic shift. So that's what I'm saying here, right?
Excellent.
It's kind of nice. You take two matrices that have this automorphism and it's preserved.
Thank
So
you.
now I'm going to look at a different kind of permutation that's involved, and I take a group of elements of order P. Now, if you haven't had any Galois field kind of stuff, this may be a little bit reach for you. But when you do that arithmetic mod P, you can find what's called a primitive element. So in the case of 13, 2 is a primitive element. And if I take the successive powers of 2, reduce them mod P, it actually goes through all the non-zero elements of GF13. Just multiply by 2, and these are the successive powers. I can talk about a subgroup of the multiplicative group by taking that primitive element and taking some number of hops. So in this particular case, I'm going to take something where I'm taking 4 hops, and I'm only talking about using the subgroup of multiplying by 3 in this case. So 1, 3, 9, 27, but 27 mod 13 is 1 again, right? So when you multiply by 3, you go around repeatedly, okay? And that's a subgroup of this multiplicative group of multiplying by the primitive element. When you have subgroups, you can use it to partition the elements of GFP. So I start with 1, and it's generated by multiplying by 3, 1, 3, 9, 1, 2, 6, 5, 2 again, 4, 12, and so forth. So this subgroup of multiplying by 3 partitions all the non-zero elements into these orbits of size 3, and it just holds 0 fixed, okay? I'm going to impose an automorphism on constituent blocks of a parity check matrix. I'm giving them a particular kind of structure. I'm going to choose this kind of permutation, a subgroup of the Galois group, of the multiplicative group, so that I get an orbit that's small. I'm going to do that to get low density. And I will define my matrices so that they're invariant under the cyclic shift. That's just saying that they're circulant matrices. But more than that, they're special circulants. They also are invariant under this other permutation of this subgroup. If you have a set of matrices that have both those permutations, they form an algebra, and you can multiply 2 of them, and the result will again have the same automorphisms. And to know that, we'll just go back and look at the proof I gave you for the cyclic shift, and I didn't use the fact it was a cyclic shift. I just used the structure of multiplying on the left by this times h and by the inverse, right? That's all I used. So I can in fact do it for both of these and it still works. So that means I can take 2 of them and I'll end up with something. Now, how do I recognize a circulant that is invariant? Well, it turns out that if you define a circulant matrix, it's characterized by the polynomial of its first row. And you can check that it is invariant if, in fact, that first row polynomial is invariant under raising to the bth power. So if I have h of x, and then I substitute x to the b in, that's multiplying all the coefficients and the exponents by b. And if that, in fact, is the same thing, it says it's invariant by multiplying the exponents by b. And that's how I can identify it. It means that the exponents in this polynomial have to appear in orbits. So here's an example for my p equals 13. I have a polynomial h of x, 1. Well, 1 is x to the 0, and if I multiply 3 times 0, I still get 0. So when I do that, multiply by 3, this one stays where it is. That's an orbit, the orbit of 0. If I multiply by 3 here, it goes over here. By 3 here, it goes here, and by here, it goes here. So in fact, h of x is equal to x to the 3. So this, a circulant that has this polynomial defining it is invariant under this multiply by 3 permutation.
I don't think we're seeing your cursor if you're moving something.
Oh, let's see. Maybe I have to go operate over here. Sorry.
Oh, there it is. Yes. Now,
Yeah,
now I
sorry.
see your cursor. Yeah.
So here's the 0. I've got my 2 screens here. Here's the 0. The orbit of 0 is just this. It doesn't change when you multiply by 3. But over here, 1 goes to 3, goes to 9, goes back to 1. So if you multiply the exponents by 3, it's the same thing, right?
You can also go down, sorry to interrupt, but at the lower left of your slide, there's a little pin icon. I think you can click on it and make your cursor into like a laser pointer or something.
Too much complexity.
Sorry. Okay.
Can
we
you see
can
my
the
cursor?
now. It's fine.
All right. Okay, sorry, I'm using the wrong screen there. Now, I'm going to do analysis of the graph by using orbits. If I have a matrix H, and now I'll start thinking about H as being an actual parity check matrix, but I think of it as being integer valued for analyzing the graph. So you just turn H into a matrix that has integer coefficients.
Mhm.
You know, every one is considered an integer. And you have a 1 if these two nodes are connected, right? But now it's an integer. If you take the product of H times its transpose, with a little bit of thinking about it, it actually tells you the number of walks of length 2. Is there a path of length 2 between one of the check I, a row, and one of the checks J, a column, in this product? And it will tell you how many walks of length 2 might connect those two. If there are no walks connecting, it's going to be 0. But if there were 2 paths, you'd see something not greater than 1. You might see 4, for example. But that would mean there are 4 ways of walking between 2 parity checks. If you saw in this product, you saw a 4 in the off diagonal. So the graph will have a girth greater than or equal 6 if all the off diagonals of this product of integer matrices are either 1 or 0. They can't be 2 or greater, because that would mean there are multiple paths, and therefore there is a cycle of size 4. So I can analyze that graph. When I choose an H that has invariance under these 2 automorphisms, when I do this multiplication, and every one of the blocks has got the automorphism, then all the product elements will have that automorphism. And you will know that the exponents will appear in orbits. I didn't really use the fact that it was a binary matrix back there. You can have an integer matrix and the same things go along.
Can I ask a question?
Sure.
So if I extended this idea and multiplied the H's more times to get more walks, would the cycle links actually show up on the diagonal? Basically, the counts on the cycle would be the counts on the diagonal would correspond to cycle links, or am I misunderstanding?
No, the diagonal kind of, it talks about walks where you go out and you come back.
Exactly. Yeah. So a cycle.
Right. But eventually what you'll see is that you'll have an entry that where you get greater than 1 occurring in an off diagonal. And that's the first time where 2 distinct different nodes suddenly have 2 paths between them. And that means you've got a cycle. So you continue to do just what you said, Rick, which is you can multiply these. And as long as you're only getting 0s and 1s off diagonal, you haven't yet found a cycle. But the first time that you say, like after 4 multiplications, oops, I see an entry that's 6. That means there's 6 paths that both made it to that same spot. And so there are multiple cycles that run between those 2.
Oh, okay. It's about actually, so having a 2 on the off diagonal means there are 2 distinct paths.
2 distinct paths.
And that's what makes a cycle, because it's not interesting to say that walking out to a node and then walking back along the same path. That's not a cycle. Got it.
Right. And you can also ask yourself another question. How many multiplies do you have to do before all entries are non-zero? And that will tell you how long a walk do you have to go to get to the most remote outpost. Starting from one parity, there's some distant bit over there that we haven't seen in days, right? And it took a long walk to get there. So you can analyze these matrices if I'm using as building blocks, things that have these two automorphisms. It makes it much easier to analyze these. So here's the first example, and I don't think I've got more than just a couple of deep coding people who would recognize the algebra. But here's an example. I take p equals 73, 5 is a primitive element. So if you do a raster scan up here, you're getting all the successive elements in GF 73. Just multiply by 5, multiply by 5, multiply by 5. I'm going to take a subgroup, which is only taking the 8th power of 5, which is actually the number 2. So if I take the number 2, multiply by 4, I'm leaping through this thing, big hops through the group, and then I come back to 1, okay? That forms an orbit of size 9. You can see it here. And I'm going to take a circulant matrix. In this case, the circulant will be the parity check matrix. I'm in a big square matrix, right, a circulant. But it's going to be a special one where h of x has got as exponents 1, 2, 4, 8, 6, and so forth, all the numbers that are in this orbit. Okay. When I do that, and I do this multiplication, I know that the product has to have its exponents appearing in orbits. So I can check what happens. Well, you get 9 on the diagonal because this has got 9, and so you go out and come back, you got 9, right? That's the diagonal says you got 9 connections to every one of these parity checks. But when you analyze these, it actually turns out to be pretty simple because this one has got the minus sign and this has got the plus, and all the cross terms, -1 times the 2 will give you 1. When you get the -1 and the 4, you'll get 3. When you get the -1 and the 8, you'll get 7, 15, right? So these are the orbits that appear in the product. And in fact, I've laid them all out here. Those are all the orbits that appear in the product. And now when you look at which orbits have those numbers in them, there they are in orange. In fact, it's got all of the orbits. Okay? So in that product, you've got all of the orbits. So the form of this product is very special. It's got all of the orbits and they appear exactly once. So it's an identity, it's an all once matrix with 9s down the diagonal, not ones, is what you get. And it's easy to arrive at that using this kind of orbit analysis. And from the fact that it didn't get any off diagonals that were greater than, that were 2 or greater, you know that the graph has got girth 6. In fact, I can rapidly argue that the diameter must be 4. You can get any place to any other node in 3 steps. The bits are degree 9. The parities are degree 9. You can do a simple tree bound that will say, well, you got a top node and then it connects to at least 9 distinct bits. So it's got to have minimum distance 10. And so you've got that. But now I can show you if I take h of x and I square it. Well, I said this, I've chose this so that it would be invariant under multiplying by 2. So h squared of x is equal to h of x, which says h of x times 1 plus h of x is equal to 0. And if you figure out what that means in terms of circulants, the first column of this matrix is defining exactly what that's the equation is telling you. And what that says is I can give you a code word of weight 10 right there. There's a minimum weight code word that in fact is showing as orbits of this multiplied by 2 permutation as well as being cyclic. And if you are an old-time coding theorist, you'd say, oh, I recognize that. It's the perfect difference set code. Okay. So there's a very strong code. It just turns out that when you do algebraic constructions, you very often will end up with redundancy in the equations. depending on how you do it, you can easily end up with redundancy in the equation. Here's a strong example of a very good code that has perfect graph, so to speak, and comes right out of constructing by orbits. So here's a template for what I'm going to do for my codes. And it's got this simple form. It has to be at least 2 by 3 if you want to get something that's sort of non-trivial. You've got to get some multiplications going on, so that's why it has at least 2. It has this simple form, and I'm going to take P by P circulants. I'm going to take a subgroup. Depending on what subgroup I use and how I choose these constituent circulants, that will tell me about the density of the code that I'll end up with. I'm going to choose it in such a way according to some subgroup of the multiplicative group of GFP. I'm going to assure that all of the exponents are appearing in orbits of that permutation multiplying by B. And I'm going to select the orbits to make sure that I don't get a girth that's under 6. And I'm going to try to minimize the diameter of the graph that results. Minimizing the diameter is making sure that information flows very rapidly across the graph from all points to all other points. So information from one bit will flow in diameter steps to all other bits. And if you can minimize that, you're in effect getting very fast flow across the graph. So small diameter is in effect, speaking broadly, enhancing the independence of the information that's traveling during decoding. And I will also note that if you have a circulant that has weight 3 or greater, you're guaranteed to have a girth that is 6 or less. So if I'm talking about a weight 3 for this polynomial or this one, any of them, then I'm sure that I will have a girth of 6 or less. And that's what I'm concentrating on here.
Excuse me, I would want to see what is the diameter in definition?
Oh, it's the shortest path. Take any 2 nodes in the graph, find the shortest path. Now maximize over all pairs of nodes. Okay. So here's what you get for that form of h of x when you do this multiplication. And I know that all these orbits are going to be polynomials that occur with exponents occur as orbits. And I'm going to choose these polynomials in that template I gave you so that I don't get anything less other than girth 6. That in the product, I don't get off diagonal elements where I get a multiple of 2 or greater. All these off diagonal elements, including in these matrices, the off diagonals have to be 1 or 0. So here's an example. I'm going to take the orbit of 2 under multiplication by 3 for this one. I'm going to take the orbit of 1 for this one and for this one. And I'm going to take the orbit of 0 for this one in that template I showed you. Produces a 391410 code. The very best code known in algebraic coding theory, if the tables are up to date, and I think they are in this case, has minimum distance 12 at this spot. So here's a code that's very sparse. I can figure out the weight of it, how many connections are there for a bit in this circulant, in this block. Well, there are 3 plus 1. So there's 4 connections here, 4 connections here, and 4 connections here. The bits have degree 4. The parities, I just go across, and here this parity has 3 plus 2 plus 1. That's degree 5, and up here I have degree 7 for those parities.
Don't forget to bring your cursor under that.
Yeah, sorry. So this looking at the columns, I have 3 plus 1. That means these bits in this block are by 4. This block has got 4, and this block's by 4. All bits have degree 4. The parities in this lower block have 1 plus 3 plus 1, that's 5. And in the upper, they have degree 7. Okay, so I know what the parity degrees are by virtue of how I chose these things. Now I select orbits, and I can do it. I won't. We don't have time for me to go into this at this point. But it's actually turns out to be pretty simple because of the way these things work out. I figure out what are the orbits that appear in this product. If A is this orbit here, then I get these two orbits from A times the reversed form x minus 1. I can figure out what I get for B. Well, that's really simple. If I figured out A, I can figure that one out just immediately. Similarly, I can get C and D. So I can figure out these orbits, and I can choose the orbits so that I don't get an off-diagonal term that will indicate a girth 6. I mean, less than 6, that would indicate girth 4. And I just have to select those. So those are the ones that appear here. This term A will give you those two terms. B will give you the other. Well, that means in this sum, I've got all the orbits, in fact, just as I did in that perfect difference code. Now over here, I get this orbit and this orbit here. Those are distinct, and this orbit here. I've got, this one has got 3 of the 4 non-zero orbits in it. And similarly, this is just the reverse of them all, the negatives of all these in mod P, and here I can go D and so forth and so on. So I just chose those, and so they pack, I selected them so they sort of pack the space nicely and never have overlap with multiples. So these are the kinds of codes that I was able to produce, though I had to use the tools to do the analysis. I can actually design these codes pretty close to by hand. I got an 113822 code. It was this code that caused me to say, oh, now I'm paying attention, because that's very close to the best known code in terms of its minimum distance. The best known code had 24, and here I have a very sparse code that has 22. So, hey, this is working for me, right? This looks like it's doing what I wanted it to do. And then I designed another code, and I'll tell you a little bit later on, where I lowered the degree. I got rid of the bits of degree 6 and I dropped them down to 4 by simply using d of x equal to 1, a lower weight. The original d of x has weight 3. This one has only weight 1. That lowers the degree. And that, I'll show you why. Did another code of length 303. I think its minimum distance is 50, but I don't have a proof of that at this point. And you can see its parameters. And then I did one that would be longer to see what would happen there. If you had the best code node, you might you'd get something at least in the 170s for the minimum distance. But 144 is not too bad, you know. It's very, very sparse code. Okay, I got in contact with my old colleague and friend from long ago, Dariush, and said, hey, do you have any ability to do simulations? Because I'm not tuned up for doing simulations. So he did simulations and also created a code that would be right in the same ballpark. And he can tell you more since he's here about how he did that. We're going to run out of time. But I said, let me see what happens. He came up with another code. I said, let's see what happens if I make the code sparser. So I dropped the degree of one of the sets of bits. I dropped the degree from 6 to 4 in that last block, and the minimum distance went down. But in terms of the waterfall region, the performance went up. It performs better because it's lower density. Then he came along.
Wait, can you tell us, the legend, I can't see the colors. Can you just?
Okay. So the red one is a 22 code, right? Just 2 less than the 24 of the best known code. The black code is.
Oh, I guess I can see those colors. I'm just trying to figure out what the blue curve is.
Oh, that's a lower bound on what's required, and Dariush knows it better than I do. So
that's that the whole box there is I'm sorry, now I get it. The box that starts with normal approximation, that is an entire description of the blue curve, right?
Right.
And then I know exactly what's going on. Thanks a lot.
Okay. So then he came back and said, well, I can do a PBRL code. And he gave me the code, and I've used Magma, the software that's very powerful, to find its minimum distance. And I was really impressed that he got a minimum distance of 21. And his new PBRL code was right down here. Okay. So, okay, wow. And it's even got a better minimum distance than the one that I got algebraically. So you got a very powerful technique there. Now he used this protograph that gives you this ability to make it rate compatible because of the 0 here. And it has a subcode, which is 74388. I don't know if that's of interest to you people.
Well, can we I mean, I'm interested in, Darius, what's the connection between your PBRL code and Michael's automorphism codes?
What I did essentially for high rate, I restricted, degree to before in order to get good, not as observing error floors. And then I optimized, used 2 and 2 here in order the threshold also be small enough. Although threshold is not, is not the only criteria for the small codes. The minimum distance is also very important. So then I used just CPEG without going through algebraic type construction that Michael presented. But PBRL codes are very good codes. I talked to Michael, see that if he can come with algebraic type structure, the same method that he presented here, to get better PBRL codes. And most probably he can do that.
Yeah, could you give us a
Need
better
his
high
help
rate?
really in this.
Specifically, you're saying to use the PBRL, to use the automorphism structure to get the high rate code, and then we would generate the incremental redundancy the way we've always done, or are you thinking there's an
And then using threshold, I'm saying not the only criteria, but it's good to have a low threshold. But then if Michael can use his algebraic method, maybe we can get much better PBRL codes.
Okay. All right. Sorry to interrupt. Keep going, Michael.
It's okay, as long as you're not going to lose everybody. I can go a little. So here's a rate 1/2 code, just to show you that it's not rate 1/3 only. Same kind of structure, p equals 37. I choose lightweight, degree 3 polynomials, degree 3 polynomials here. And so 3 + 1, 3 + 1, all the bits have degree 4. I select orbits so that when I do this multiplication, I can go through in terms of say, oh, I got distinct orbits here, got distinct orbits here. So much easier if you got the orbits, because you don't have to check the whole thing. You just check the orbits, right? And the orbits have structure to them themselves that makes it much easier to do this. And that code I was able to construct, and so it doesn't have a girth of 4, it has girth 6. And that code is a 148.74.18 code. The best known code has got 22 here. But here I've got bits of only degree 4. Parity is great. So this is a regular LDPC code. So that's just to show you can do it at rate 1/2. It's not rate 1/3 was just my test bed sort of. Don't have time to go over this in detail because we're about to run out, but Darius said, well, we could like this rate compatible. And I said, well, I think I can do rate compatible style codes. So I did a code that had this structure, again, using weight 3 polynomials. And I set out to be sure that at every step, as I added redundancy, I'd hope to get a minimum distance that was good. So the first starting code, if you only use circulants, it's going to put a strong bound on what minimum distance. You can't have a really sparse code and have a good minimum distance if you only have the circulants. So the base code here is a 5738 minimum distance 6. The best code would have 8. But then I increased it to a code that is got 19, I'm using p equals 19 more bits, and got an 11 code. Well, the best code has got 14 of all algebraic codes. Then I could add 17 more bits and I could get 17. The best code has got 20 of all algebraic codes. And then I end up with a 114.38.24. So it's got a big minimum distance, right? But I was doing this with the idea of making sure that I'd have small diameter, and hopefully the weight wouldn't go up too much. But you end up with bits of degrees 4, 7, 6, and 3 on this. I can actually change this to 1, and I could drop it down here, and you see the parity degrees. And I check this matrix on the orbits, and that's what it looks like. HH Transports has this, and all the matrices involved will have that invariance to them. And then I do the simulation result, and simulation result says, well, this code with minimum distance 24 in the waterfall region doesn't do as well as the weight 22, and nowhere near as well as the weight 20, or the one that Dariush designed. And I think the simple answer is it's got it's got too much weight already. Even though it's comparatively sparse in the world, it's just got too high weight. And you folks probably would know that from looking at the weight distribution and the profile that I've generated, that probably was going to run into a problem in terms of the algorithmic convergence. But you can do it. I just thought I'd show that. So I'll just conclude. My technique is to impose this group of automorphisms that clearly can give you a lot of flexibility in construction. You have to, if you want to get girth greater than 6, you can only use weight 1 or weight 2 polynomials. I have used that on some other codes to get girth 8, for example, just to know that I know how it works. The minimum distances can be excellent, I'd say. And I've got an intriguing sort of observation. Every time I've done one of these codes, it turns out that there is a minimum weight word. When the software Magma has found a word, there's been a minimum weight word that exhibits the invariance under the multiplicative automorphism group. And if I could prove that mathematically, I'd be able to extend when you can say what the minimum distance is to very much longer codes, because it says you just have to check a subcode to find the minimum distance. But I need to do more understanding of how the belief propagation will work. And I want to thank the people at John Cannon and the computational algebra group at the University of Sydney who did this software system, Magma computational algebra system, that I used extensively, that really got me going on this, because you can do marvelous things. And then Dariush was kind enough to get me into this by doing simulations that said, okay, we'll come to reality. Those are very sparse codes, but still not sparse enough. And so you have to go back. So you've seen my first attempt at those PBRL codes, and I suspect that understanding how sparse they have to be, I can do a little better, but we'll see. So I'll stop sharing with that.
Okay, let's go into gallery mode, everybody. And we can, what I'm gonna do, it's 10 o'clock, so if you have to go to a class or something, you can feel free to leave at this time. But I'd also like to give Michael a hand, and then we'll go into some questions. So thank you very much. That was great. I really appreciated it. And I have some questions, but I want to open it up first. If you have a question, you can go ahead and raise your hand or just talk. Either way is fine with me. So Lev, did you want to ask a question?
I'm still trying to formulate my thoughts, so you can go first.
Okay, so we're going to do like a recorded question session, and then we can have a more informal discussion in a few minutes. So I guess the question I'd like to ask is, so actually the block length 128, like rate 1/2 codes 68, 128, that's kind of a place where people are certainly are currently like, there's a battle there. There's a lot of people trying to find codes right in that range. And there are some codes that actually get really close to the random coding union bound. And then I guess I'm wondering where you see this approach. Do you think of it as primarily in the block lengths of 100 or 200? Or do you think we could also be looking at block lengths of 500 and maybe 1,000 and even up to longer block lengths? Where do you see in terms of block length this as being, could it be applied anywhere?
Well, I think it can be ultimately applied anywhere. It says you're restricting yourself to a somewhat simpler world than the random world, right? you said, I'm going to use this discipline of orbits, and it just turns out that the discipline of orbits doesn't seem to block you from getting really good codes. So, so far on these small codes, these very short codes, I guess you call them nowadays. They used to be fairly long back when I started, but now they're short. It really puts a huge premium on having very, very low weight. I'd be interested. So I did, one of the examples was a code of length 1,000 rate 1/3, just because I was working on rate 1/3. So that the bits have degrees 11 and 22 in that code. Now, out of 1,000 length bits and 600, parity checks, is 11 way too much? And you folks who know about the profiles and what you have probably know, you might be able to say that profile is not good enough to get a good code at length 1,000. But I can do other codes. You can use the algebraic technique to construct all sorts of codes. At the end, will you be able to prove the minimum distance, or what can you say about the minimum distance? And right this moment, I can't give you a mathematical definitive answer because I haven't proven this conjecture. But I think
there's a lot of interesting work to do, bringing together, it seems like we can bring together density evolution analysis of degree distributions along with the algebraic approach of constructing these orbits. But then the other thing that's really interesting is simulating the codes and showing how well they do as compared to the random coding union achievability bound, or this other thing, the meta converse. There's kind of like a banana between these two curves of the random coding sort of lower bound on achievability or upper bound on probability of error, and then the meta converse, which is a lower bound on the probability of error. And if you can get a code that lies in between those two curves, you can kind of declare victory because they're kind of tight. And so that's, to me, it would be really interesting to think about, where does this approach, in what block length region can this approach get you close to those bounds? And I think if we bring together those, all those, we can juggle all those balls, I think there'll be a really, it could be really powerful. So, okay, other questions?
I just wanted to say that, Bonavasic and Lara, they had other commitment. They send me messages that they cannot come, but I guess Nathan should be postdoc of Bonavasic. Is it right, Nathan?
Yes. Yeah.
Yeah. Okay. Thanks for coming.
No problem.
But I have another question, from Michael, that everybody is sticking to GERT 6, whether it's better to go to GERT 8 or 6 is enough for the, constructing LDPC codes.
Well, I think I would be tempted to say that you probably are going to want to go to larger girth if you're talking about long codes, because eventually you want to have the full power of the tree. I mean, you want to have a bigger tree than you get out of girth 6. Now, when you have these very sparse and you're only using weight 3 and you have some cycles that close, I don't know. It's a question of whether or not the belief propagation can handle that if there's such an infusion from elsewhere that it swamps out the problems with the girth 6 that exists. You can use this technique, and I can't go into it here, but you can create things that have an automorphism that allows you to do similar kind of analysis and has girth 8, and you can do bigger girths than that. But I'm not well versed at doing it yet. I did one example at girth 8 just to satisfy myself I knew how to do it. But you can do it.
But I mean, there's also this perspective that from our group about ACE, or approximate cycle extrinsic message distance. In other words, that it's okay to have a small cycle if that small cycle is sufficiently connected to the rest of the graph.
If I went back into that 1,000 code that I mentioned, where the bits have degrees 11 and 22, it's got a diameter, it's got a girth of 6 because it's got weight 11, so it's decidedly got girth of 6, but it has a diameter of 4. Now you have to know what that means. It says you start at a bit, you go out to parities, you go to the next one, it's all distinct bits. And then when you get to the next level of parities, you've got some that close because that's girth 6. One more step and you've gotten to every other bit. So when you talk about, does it get in, I can't remember how you phrased it, Rick. There's a place where it's only one step away from every parity, right? That's why I'm talking about trying to minimize diameter. And you probably have optimization once you've gotten to the smallest diameter that you can get.
That's very exciting. I guess I also have this question about, so we did kind of drift away from caring about minimum distance. And part of it was because of the difficulty of computing it, but there's also an aspect where for a long enough block length code, it actually does become less important because, especially like for example, with turbo codes, you can have a small distance, but it has a number of nearest neighbors equal to 1 over the block length, not over the, you can think of nearest neighbors for convolutional codes where you say it has a nearest neighbor of 4, but it's actually 4 times roughly the block length. Okay, so there's a huge number of those neighbors. And so it's very important to get that distance to be large. But with turbo codes, you don't get that kind of like I have a neighbor every shift. So sometimes, you can have a good code that has a small nearest neighbor, a small dmin, even though, because of the number of nearest neighbors is 1, like the probability that that particular error happens is small.
Right.
I'm wondering about whether you feel like with your codes, you have that structure that, well, if I have whatever the daemon is, there's a lot of them. Or sometimes you could have that behavior of turbo codes where you can have a rare small distance.
Yeah, I think it's something that's worth exploring. The general characteristic is because you've created an automorphism deliberately, you're going to get an orbit, right? But compared to the scale of the graph, that orbit may not have that many members in it either, right? So it's not, if you do random stuff, you can say, well, I had one random event that wasn't very good. I had a kind of a weak spot, but I don't get a lot of them. And so it's okay, right?
Yeah.
It washes out. My hope was that you could get something where you would have your cake and eat it too, right? That you have a very good minimum distance and you may have an orbit at that, but it's a really good minimum distance, much better than some other things you might encounter like those turbo codes.
So I guess to me, like that's one of the exciting tensions right now is, does that work? Like, can I get, if I want to have a code that performs close to the random coding union bound, must I be doing something that has this behavior that I've cleared out most of the nearest neighbors, but I have a small distance? Or can I get there with an algebraic structure where whatever the minimum distance is, I actually am going to get an orbit of it, but it's fine because it's so good. Yeah.
Yeah, I don't see myself, I don't see any reason that you would have to have some of those aberrant events in a really good code. I just don't see that. Now, one of the sort of comeuppances that I got was understanding that the belief propagation algorithm, if you have a beautiful balanced structure, it actually causes the algorithm to not be able to know which way to turn when you get near a boundary, because it doesn't know how to converge, right? It's kind of saying, when I try to explain this back, explain it, I say it's a little bit like supercooled liquid. You can have a supercooled liquid that's below the temperature of freezing, but it doesn't know how to freeze. All it takes is something that allows it to know how to nucleate, and suddenly the whole thing will freeze, okay? And a little bit in the algorithmic behavior, I think that's what's going on. When you have a few bits that can get started, then you say, okay, now I know how to solve the rest of the equations. But if they're perfectly balanced, it's just they're kind of groping for which way to turn, right? That's the phenomenon. So, some of these that I've done may be too regular, or too balanced, and they're kind of beautiful mathematical objects, right? They may have that problem, but I don't think you have to abandon it to be able to get where you would want to go.
Oh, actually, this brings something else up. If you're thinking that perhaps the issue here is that you've got a really good structure, and we know it's really good, but the current belief propagation that you're doing is somehow held back from converging. Lin Fong in the red sweatshirt has been working on some fun, and we have some results for small codes and longer codes, where you can actually use machine learning to not do the standard belief propagation, but instead design the weights sort of in a bespoke fashion to get that thing to converge when, without, I guess, to solve that problem of the supercooled. There's no reason that you have to do it in a perfectly balanced way. Having a little bit of asymmetry makes the algorithm work better. And we've actually seen, significant, for a very short code, like moving it several tenths of a dB, half a dB, by just changing the weights on the message passing. So that it could be really fun for us to do this with the codes that you've designed. Maybe they're better than your current simulations show.
Yeah, that was another thing out on there. I say, well, belief propagation, it's beautiful. I mean, I proved in my paper, right, that you're doing optimal on a tree, right? Okay, but the world isn't tree. So now what happens when it's not a tree? And it made me say, well, you got to change it. Actually, that 73 code, I think that was probably the first code that was implemented in hardware. We did in the mid 80s, we did a VLSI implementation of the decoder, but we did min sum because back in those days, you couldn't fit the whole code onto one chip easily. Nowadays, I think it's trivial, right? Almost 40 years later. But we did it, and we were playing around with how many bits did you need. You can play around with the algorithm a lot, is what I'd say. So belief propagation has, and what is the precision you're using? For example, that's another issue that people look at. And you can do modifications.
You know what? I think that those two, even though, okay, so that length 74 code has been around a while, but I think it'd be a great target for us to look at this, like machine learning and multiple precision. That's an area where we have a lot of expertise in terms of getting to see like, well, how well could this code work, if we approach it from this perspective, saying, well, we know it has some cycles, and let's figure out like what's a way to find the best decoder for this code. And maybe that could unlock some hidden potential of your approach in general.
Yeah, possibly. That'd be very interesting.
Great. So yeah, go ahead, Nitin.
Oh, I had a question regarding the condition on the orbitals for girth 8. Is it already in the paper which you have in GlobeCom, or is it something which is out in the open and like something very interesting to do?
Yeah, no, it's, I was working on this, started in August of last year, and I got Magma. So I want to say thank you very much to Magma, because Magma allowed me to play with this stuff. And I said, okay, now I've got a tool I can run on my Mac that I can do this as I'm a home researcher, right? And started working on it. And I reached a point, I said, well, okay, all these, the natural easy orbits that, in the right framework, where you see the invariance within the submatrices. You don't there are other ways you can do codes that have the invariances, but you don't see them so readily as I've shown you here with the submatrices. Let's see what I can do on girth 8. And what I found was, and it's no surprise, I have this tension. If you start making things slimmer, lower weight, do you get the good dmin, right? And I came up with a family of codes of length 200 and I can't remember now what it was, but I got girth 8, but I wanted to get girth 8, I had to make it very light, right? And the minimum distance dropped from 36 to 32 to get there. So in the waterfall, it may have been stronger, right? Mm-hmm. I haven't done simulation on that particular set of codes. So I haven't developed. My friend Dan Costello said, well, why don't you think about applying to GlobeCom and we can go to that together? And I said, oh, okay, I'll work on doing that. So then I did all those rate 1/3 codes and did some kind of drop the general approach where it's easy for me to get lost having fun.
Thanks a lot. Yeah, and one more follow-up in the sense, like, is it so you had like different codes, which is rate regular, regular, and also. So I was thinking, enforcing condition on the parity check degree or those kind of things are easy for, I mean, for this framework with GERT 6. So I want to pick some codes which has say parity check degrees are regular, but DV could be the degree of the variable nodes could be different. Just I don't want too many degrees, but like what you have shown, like, so for example, in your case, you had like degrees 5 and 7 on only, right? So
Right.
those codes, I mean, I think this method is really nice to like construct such codes where in a what do you say, like not, yeah. I like the how the codes were constructed, and it is like kind of suits what codes I really want to use for the things. Yeah, so it's
Yeah, well,
it's very interesting.
I wanted to show in choosing the rate 1/3 to study, I wanted to show you I could get two different weights for the bits, and with the hope that maybe you would actually, that would help the convergence.
Yeah. So it kind of like goes with what Professor Wessel was saying about like to break the asymmetry. It kind of helps sometimes having that slight different degree in the variable nodes itself can help sometimes to break that symmetry.
I think it would be fun though to have an understanding of what the ideal degree distribution should be, and then bring your automorphism structure to bear, knowing that you're trying to hit certain degrees.
Right.
Because I feel like if you have a code that has both the right degree distribution and a great minimum distance, then both classical and modern coders will agree it ought to be a good code. So that would be fun to see that, to bring those two things together. And I think that's something we could easily, I think it's something we could do. Yeah. Well, super. Any other questions?
Hi, I had a few questions. So you kind of mainly did a lot of plots on the waterfall, but my group, for example, is interested in storage. So we care a lot about like the airflow properties. Did you do any kind of simulation results for that to determine how will these graphics work on there?
No. As I mentioned, I was entirely dependent on Dariush Dipsalar to do the simulations, and he did the ones over the waterfall region. I guess because it would take a long time.
Yeah, it takes very long time, but I believe that you will not see any error flows with using Michael's code. I don't know, at least done to the 10 to the minus 15 frame error rates, but it's hard and takes very long time to simulate at 10 to the minus 15 or 14.
But we're welcome to, if you guys want to do those simulations, I think we have the code, so you can.
Yeah. I'm curious about that because we do some new research about how cycles, when are concentrated together, are major contributors to like stuff such as absorbing sets, trapping sets. And so if you're minimizing the diameter, is it likely that now a lot of cycles are together? And maybe this is a contrary force, because if a cycle is isolated, it's not going to create an absorbing set if your degree profile is sufficient. So it's interesting if there's something here about that.
Yeah, well, this, that because they've got this mathematical structure in this automorphism group, generally speaking, you either turn out to be a big winner or a big loser. I did something, I said, ooh, well, I can choose this orbit and this orbit, and it just fits perfectly, and it just fits perfectly to be entirely bad.
Okay.
I mean, that's when I was first doing it. I'm going, oh, this would have a beautiful symmetry, and the symmetry is such that it's got a terrible code. It's just not a good code. So I don't know. I guess in Dariush doing the simulations, he found some on the code that had minimum distance 22, Dariush, you mentioned that you had some pattern of 7 or something that showed up it was 7 errors were causing some problem. But I don't know that we got an extraordinary density of.
I think the area there, the opportunity is that Lara's group has pioneered a variety of ways to represent those absorbing sets and trapping sets using mathematical expressions and equations that you can check to see whether they're there. And it seems to me that when you describe the code itself using these orbits and equations, that you might be able to get sort of an analytical investigation to say, oh, by the way, we were worried about the following 12 trapping sets for this block length. And we know they aren't there because we have these equations describing all the automorphisms. Or actually, we know they are there. We can see them. I think that would be an area where could be some really fruitful collaboration between the expertise in Lara's group and what you're trying to do.
I have something to add, like to see the error flow. So during my PhD, I have developed this method where you don't have to preemptively see the trapping sets or understand if it is harmful for your decoder or something, but it's more like an efficient method to understand what are the harmful trapping sets. It's basically an expansion contraction method. So you start from these most probable cause of error, which is the cycles. And here in your case, you have the girth 6, right? So from these girth 6 and girth 8, probably you can do some expansion and do a contraction based on which decoder you're using. Like, for example, you can use the belief propagation or min-sum. You can choose the decoder or finite alpha decoder or something. And then it basically it gives you out the list of error patterns, most harmful error patterns, and thereby the trapping sets also. So, and it can give you the most harmful trapping sets. And in your case, with having the automorphism groups, I think identifying you can significantly reduce the complexity of finding these, because if you find one of them, the other patterns just come back. If one, it's like in quasi-cyclic code, we have one error pattern, all the circlants also are an error, right? So it's much easier to do it for these quasi-cyclic codes. And I think then we don't and then you have to then do your orbitals, modify the orbitals to reduce or to eliminate that particular configuration.
Right. There's probably a lot. I mean, when I was doing this, I kept saying, once I kind of understand this better, I'm sure that there are strategies that should be used in how you pick these orbits. Some of it kind of comes naturally to you. You say, okay, this is why I know I should be doing these orbits, and it's pretty straightforward. It just feels like this is the right answer. But I didn't try. I don't have the wherewithal readily available for me to try optimizing thereafter on the places like on the length 1,000 code. I didn't do optimization over why would I pick exactly that versus that, and you've got flexibility in there, so there's room for optimization.
All right, I think we've probably gone to the end of the official question time. Let's go ahead and thank Professor Tanner one more time. Thank you very much. What a fantastic talk. I'm going to give you my virtual applause as well. There it is. Okay, and I'm going to go ahead and stop the recording.